Welcome to the deep dive. Today, we're really diving deep, tackling one of the absolute monuments of scientific thought, Albert Einstein's paper, The Foundation of the General Theory of Relativity. Now, this is famously complex stuff, right? So our mission here is to sort of cut through that complexity, pull out the really crucial insights, maybe some surprising bits too, and leave you feeling genuinely well-informed without getting totally bogged down in every single equation.
Exactly. And it's key to understand this wasn't just like a small step. It was a massive generalization of his earlier special theory of relativity. It really built on the work of mathematicians like Minkowski, who had shown this beautiful connection between space and time. And the main mathematical tool, this absolute differential calculus,
Right.
that heavy lifting had already been done by giants like Gauss, Riemann, Christoffel. Einstein needed those tools. And he always stressed how vital his friend Marcel Grossmann was.
Mathematician.
Yeah, Grossman was absolutely crucial in helping him navigate the really difficult math and actually finding those gravitational field equations. Couldn't have done it without him, or at least not nearly as quickly.
Okay, so that sets the stage. Let's get into the why. What drove Einstein from special relativity to this much bigger general theory? Maybe let's quickly recap special relativity, STR.
Good idea. So STR, its core postulate, is that the laws of physics look simplest in a specific kind of reference frame, one that's not accelerating, what we call an inertial frame, K. And they look the same in any other frame, P prime, that's just moving smoothly, uniformly relative to K.
But that's the catch, right? The special part, it only worked for uniform motion, no acceleration.
Precisely. And this limitation, it wasn't just inconvenient. Thinkers like Ernst Mach had pointed out what they saw as an epistemological defect in physics up to that point.
Epistemological defect, meaning like a problem with how we even know things about the universe.
Exactly. Both classical mechanics and STR relied on concepts like absolute space that weren't directly observable. Einstein, influenced by Mach, felt that was unsatisfying. Physics should be based on what we can actually observe. He used this great thought experiment to illustrate it. Imagine you're in totally empty space, far from everything. You have two identical bodies made of fluid, S1 and S2.
Okay.
They're rotating relative to each other.
Yeah.
Now, let's say S1 looks like a perfect sphere, but S2 is bulging at its equator. It's an ellipsoid.
Ah, like the centrifugal effect is squashing it.
Right. But if you're on S2, you see S1 spinning and S2 is stationary. So why is S2 squashed and S1 isn't? There's nothing inside the system of just S1 and S2 to explain the difference.
Okay, so what's the Newtonian answer?
Newton would say there's this absolute privileged space, call it R1. S1's at rest in R1, but S2 is rotating relative to R1, and that's what causes the bulge.
But you can't see R1.
Exactly. It's what Einstein called a factitious cause, a made-up reason. He argued the real cause must be observable. It must lie outside the S1, S2 system. It has to be related to all the other distant masses in the universe. Those distant stars and galaxies, they effectively define the rest frame, not some invisible absolute space.
Wow, okay. So if there's no truly special, privileged frame of reference.
Then the laws of physics shouldn't care what kind of motion the reference frame has. They should work whether it's moving uniformly or if it's accelerating.
And that's the jump to needing general relativity. It
Yeah.
has to handle acceleration.
Yes. And there's a crucial physical fact supporting this. Imagine you're in a closed box, accelerating upwards. Everything inside falls to the floor, right?
Uh-huh. Feels like gravity.
Exactly.
Mm-hmm.
And importantly, everything falls with the same acceleration, regardless of what it's made of. A feather and a lead weight if you ignore air resistance.
Just like gravity.
Precisely. This observation, that acceleration mimics gravity. And the fact that gravity causes all objects to accelerate identically, something verified with incredible accuracy by experiments like those by OTFAs, this equivalence is key.
So changing your coordinate system, like accelerating, can actually look like you've turned on a gravitational field.
That's the profound insight. It suggests acceleration and gravity are deeply connected, maybe even two sides of the same coin. And this connection paved the way for GTR to become fundamentally a theory of gravitation. It also immediately tells you that the constant speed of light from STR needs a rethink in accelerating frames or near-gravitating bodies. A straight light beam in one frame might look curved in another.
Okay, that's the why. Let's move to the how. This sounds like it requires a pretty radical rethink of space and time themselves. Classical physics, even STR, you could sort of picture coordinates being measured with rulers and clocks, right?
Yes, they had a direct physical meaning. A coordinate difference meant a specific length you could measure with a rigid rod or a time interval measured by a standard clock. GTR had to abandon that simple picture.
Why? What breaks?
Okay, think about that rotating disk again. System K prime rotating relative to a stationary system K. Imagine trying to measure the circumference of a circle on the disk using a small measuring rod that's at rest on the disk.
All right.
Now, if you look at this from the non-rotating system K, that rod on the circumference is moving. So according to special relativity, it should experience a Lorentz contraction. It gets slightly shorter in the direction of motion.
Ah, okay.
But if you lay the same rod along a radius of the disk, pointing towards the center, it's not moving tangentially. It doesn't contract in the same way.
So if you measure the circumference with the contracted tangential rods and the diameter with the uncontracted radial rods.
You'll find the ratio of circumference to diameter is not pi. It'll be slightly greater than pi.
Whoa. So Euclidean geometry, the geometry we learn in school, just breaks down on a rotating disk.
In that coordinate system, yes. The spatial relationships aren't Euclidean anymore. And it's the same with time. Put a clock at the center of the disk and another identical one on the rim.
Okay.
Viewed from the stationary system K, the clock on the rim is moving, so it ticks slower than the clock at the center. An observer on the disk would also notice this difference.
Meaning the rate of a clock depends on where it is and how it's moving.
Exactly. Time isn't absolute. Its flow depends on the gravitational potential, or equivalently here, the state of motion.
This is really messing with my intuition. If our rulers stretch and shrink and our clocks speed up and slow down depending on where they are, how can we possibly define space and time in a consistent way? What do coordinates even mean anymore?
That's the radical leap Einstein took. In general relativity, coordinates lose their direct physical meaning as measurements made by specific rods and clocks. They become more like labels, just arbitrary labels for points in spacetime. Instead of demanding one correct coordinate system, Einstein said all imaginable coordinate systems are equally valid for describing nature. This is the principle of general covariance.
So the laws of physics have to be written in a way that they look the same no matter what crazy coordinate system you choose. Rotating, accelerating, squiggly, whatever.
Pretty much, yes.
I think.
The form of the equations must be invariant. This strips space and time coordinates of what Einstein called their last remnant of physical objectivity.
No objective grid lines in the universe. So what is objective then? What are we actually measuring or observing if not positions on a grid?
What's objective are the events and the relationships between them, specifically space-time coincidences.
Coincidences, like two particles hitting each other.
Exactly. That collision, that meeting at the same point in space and the same moment in time, that's a real objective physical event. The coordinates we use to describe where and when it happened are just a flexible description, but the coincidence itself is the invariant reality. All physical measurements ultimately boil down to observing these kinds of coincidences.
Okay. So how do we describe the structure of this space-time if not with fixed coordinates? How does gravity fit in?
This is where the fundamental tensor, the gain, G nu nu, comes in, is a set of 10 functions that basically define the geometry of space-time at every point.
10 functions. Why 10?
It's related to the 4 dimensions of space-time, 3 space, 1 time, and the symmetric nature of the tensor. But the key thing is these gain components do double duty.
Oh, so?
They simultaneously define the gravitational field and the metrical properties of space-time, basically, how you measure distances and time intervals locally. Gravity isn't a force in space-time. It's a curvature of space-time, described by these gain functions.
So the gain tells matter how to move, and matter tells the gain how to curve.
That's a great way to put it, famously summarized by John Wheeler. And to write laws that work in any coordinate system, Einstein used the language of tensors.
Right, you mentioned those earlier. They handle the coordinate transformations.
Yes, tensors are mathematical objects whose components change in a very specific, predictable way when you change coordinates, allowing the underlying physical law they represent to remain unchanged. He used contravariant, covariant, mixed tensors. It's a whole mathematical framework perfectly suited for this.
And you also mentioned geodetic lines. That's how things move in this curved space-time?
Correct. A geodetic line is the straightest possible path in curved space-time. Think of how an airplane flying the shortest route over the curved Earth follows a great circle, not a straight line on a flat map. In GTR, objects unaffected by non-gravitational forces simply follow these geodetic lines through space-time.
So the equation of motion for, say, a planet orbiting a star is just this. The equation for a geodetic line in the space-time curved by that star.
Fundamentally, yes. It's incredibly elegant. No force of gravity needed explicitly. The curvature dictates the path.
And what determines the curvature itself? You mentioned Christoffel symbols.
Right. The Christoffel symbols, IN, gamma tom mu nu, are derived from the derivatives of the metric tensor gen. They essentially quantify how the geometry is changing from point to point. They measure the curvature. If those Christoffel symbols are all zero in some region, it means space-time is flat there, and objects will move in straight lines at constant velocity, like in special relativity. If they are non-zero, it signals the presence of a gravitational field, causing paths to deviate.
Okay, so the symbols tell us if there's gravity locally. But how do we get the actual laws of gravity, the field equations that connect the curvature back to matter and energy?
Good question. Einstein first considered space without matter. He needed an equation that would describe how gravity behaves in a vacuum, like around a star. He defined matter broadly as basically everything except the gravitational field itself. So that includes ordinary stuff, but also light, electromagnetic fields, everything with energy and momentum. For empty space, he proposed that a specific tensor derived from the curvature, called the Ricci tensor, or a related one, G, the Einstein tensor, must be zero. Setting G E0 gives the field equations in vacuum.
Why that specific tensor?
It's like a complex derivation, but crucially, setting GEO is a weaker condition than requiring the entire curvature, the full Riemann tensor, to be zero. If the Riemann tensor was zero, there'd be no gravity at all. GEO allows for curvature, for gravity like that outside a star, which can't just be eliminated by changing coordinates. It represents real intrinsic curvature.
Okay, and what's the payoff? What do these GAA equations predict?
Well, first off, they beautifully reproduce Newton's law of gravity as a first approximation, in the limit of weak fields and slow speeds. That's essential. Any new theory has to match the successful old theory in its domain.
But it doesn't stop there, right? This is where Mercury comes in.
This is the absolute triumph. When you calculate things to the next level of precision using these equations, they predict slight deviations from Newtonian gravity. One key deviation is that the orbit of a planet isn't a perfect closed ellipse. It should slowly rotate, or precess.
The perihelion precession.
Exactly. And astronomers, especially Leverrier back in the 19th century, had known for decades that Mercury's orbit precessed by a tiny amount, about 43 arcseconds per century more than could be explained by the gravitational tugs of all the other known planets. It was a huge mystery.
And Einstein's theory.
Einstein calculated the precession predicted by GTR, and it came out to exactly 43 arcseconds per century. Bang on. No fiddling, no extra parameters. For him and for many others, this was incredibly powerful evidence that the theory was on the right track.
That's stunning. So how does actual matter get into the equations? You said G and zero was for empty space.
Right. To include matter, Einstein connected the geometry side, G, to the matter-energy side. He used the concept of the energy-momentum tensor, T, which had already emerged from special relativity. T basically encapsulates the density and flow of energy and momentum of whatever matter and non-gravitational fields are present.
So energy and momentum create gravity.
In essence, yes.
Yeah.
The full Einstein field equations are, schematically, G equals a constant, T. This equation tells us precisely how the distribution of energy and momentum determines the curvature of space-time. It links matter to geometry.
And this includes the energy of the gravitational field itself.
Ah, that's a subtle point. The T on the right side usually represents non-gravitational energy. The energy in the gravitational field is trickier to define locally, but is implicitly accounted for in the structure of the equations. What GTR does give us is a beautiful conservation law. While the energy and momentum of matter alone aren't strictly conserved in the presence of gravity, there can be exchange with the gravitational field. The total energy and momentum, including the contribution of gravity, are conserved.
So energy isn't lost. It just moves between matter and the gravitational field itself.
That's the picture, yes.
What's really striking is how this framework seems to just absorb other physical laws. You mentioned hydrodynamics, electromagnetism.
Yes. The principle of general covariance and the tools of tensor calculus provide a clear recipe for taking laws like Maxwell's equations for electromagnetism, which were known from special relativity, valid in inertial frames, and rewriting them in a form that's valid in any coordinate system, including curved spacetime. This automatically tells you how gravity influences things like light and fluids. You don't need separate hypotheses. The influence is built into the geometrical structure that all fields inhabit. It's incredibly unifying.
Okay, so beyond Mercury's orbit, what other concrete testable predictions came out of GTR?
Several key ones. We touched on rods and clocks. GTR predicts that in a gravitational field, say near a massive star, A ruler held radially would appear slightly shorter than one held tangentially, compared to rulers far away. Again, this means space isn't Euclidean near mass.
Measurable.
Extremely difficult to measure directly for rulers. The effect is minuscule, but the effect on clocks is measurable.
The gravitational redshift.
Exactly. Clocks run slower, deeper in a gravitational potential, well closer to a massive object. This means light escaping from a star loses energy, its frequency decreases, and its wavelength shifts towards the red end of the spectrum. This has been observed in sunlight and, more precisely, in experiments on Earth using very accurate clocks.
Amazing. And the bending of light.
Probably the most famous early test. GTR predicts that because mass curves space-time, light rays passing near a massive object won't travel in straight lines, but will follow the curvature. Einstein calculated that starlight grazing the sun should be deflected by 1.7 arcseconds.
And this was the prediction Eddington tested during the solar eclipse in 1919.
That's the one. Observing stars near the sun during an eclipse, when the sun's glare is blocked, and comparing their apparent positions to their positions when the sun isn't nearby. The results, though debated initially regarding their precision, generally confirmed Einstein's prediction and made him world famous overnight.
So you have Mercury's orbit, gravitational redshift, the bending of light, all these distinct phenomena explained by one consistent theory of curved spacetime.
Precisely. And the Mercury result, being a pre-existing anomaly explained perfectly, was particularly compelling. It wasn't something the theory was designed to fit, it just emerged naturally from the equations.
What an incredible journey we've taken, really trying to get inside Einstein's thinking, from feeling that classical physics was somehow incomplete, philosophically.
Right, that reliance on unobservable things like absolute space.
To building this entirely new structure for reality, where space and time are dynamic, interwoven, and shaped by matter and energy. It's just fundamentally different.
It truly is. The sheer elegance of it is remarkable. Replacing the somewhat clumsy notion of gravitational force acting at a distance with this picture of geometry of space-time curvature dictating motion, it's a profound conceptual shift.
And as we wrap up, Einstein himself left us with a fascinating thought, didn't he? He wondered if maybe gravity and electromagnetism, the two forces he understood best through relativity, might actually be enough, if unified correctly, to explain everything, even the existence and nature of fundamental particles, of matter itself.
He spent much of his later life searching for that unified field theory, without ultimate success. But the question remains potent.
So here's something to leave you with. As our understanding of particles and forces continues to deepen, perhaps through things like string theory or quantum gravity, how might that reshape our view of space-time and gravity yet again? And what other fundamental coincidences, those bedrock realities beneath the coordinate systems, are still out there, waiting for us to uncover in the cosmos?